I'm Alex Beaumont. I'm the Outreach and Engagement Coordinator at the Business and Local Government Data Research Centre. Welcome to our webinar, How Complex Networks Approaches Can Benefit Supply Chain Management, with Dr. Guven from the Essex Business School. Today, Guven will provide a brief introduction to complex networks approaches that provide insights on the relationships between the supply network structure and the response to disturbances and disruptions. He will share with you some examples and case studies. Guven will speak for about 40 minutes, and as he's going along, you can enter your questions in the question box in the panel on your right. At the end, Guven will address those questions and we will answer those that you've got. If you at any point you can't hear us, just let us know by typing in the question box. So now I'm going to hand over to Guven.
Oh, thank you very much for the introduction. I hope you can hear me. Sorry for the technical problems. So today I'll be talking about complex networks approaches to supply chain. So I will start with motivating the problem. So why are we interested in complex network approaches at all for supply chains? We will first define the network metrics and then look at their interpretation in the supply chain context. Following that, we will talk about a particular process that's called percolation process and its implications for resilience of supply networks. And then I will briefly mention several other complex networks approaches and refer you to key sources of information. Following that, I will provide a brief summary and conclusions, and we will finish with the questions. So thank you very much in advance. So let's start with complex networks. So complex networks are everywhere. So what does it mean? Actually, complex networks is a philosophy of looking at systems, reducing systems to sets of nodes, or say individuals and links between them. So for instance, we can think of mobile communication networks, human disease networks, where diseases are linked by their sharing genes, which the diseases are based on, or internet, as you can imagine. And the complex networks approach motto is the outcome of the research. The key outcome is more is different. So we cannot reduce systems into isolated parts, so the decomposability assumption is lost. So this is the idea about complex networks approach and a more general complex systems approach. And why should it apply to supply chains? So we can think of, for instance, the supply relationship management, where the focus has been on managing the diets of suppliers and buyers. But recent research has shown that the larger motifs, at least triads, are important for managing supply chain, supplier relations, therefore should be our focus. And from the very definition of supply chains, it is implying that we are actually taking a reductionist approach because we are taking it as a serial chain. But supply chains are actually networks. So basically, from a supply chain network, we are reducing it to value chains, but this might not be always valid. And actually, recent research has shown that the supply networks are actually more complex than supply chain networks. So they are not just networks of value chains, but they have more complex properties. And now we have discussed complex networks approaches and claimed that these are relevant for supply chains. Now, through two examples, I will try to convince you that the systemic effects are important. My first example is bullwhip effect. So I don't know whether you are familiar with the bullwhip effect, so it will be useful to define it. So the bullwhip effect is the amplification of demand. The distortion of demand as one moves from the retailer level upstream in the network, as illustrated in this cartoon. And this effect has been known for more than 50 years. And a lot of research has been done, but only very recently scholars have started looking into network effects. And one of the first results in this direction has shown that the serial chains cannot be actually decomposed into constituting dyads, because then the bloop effect will be underestimated. The bloop effect on a serial chain is more amplified than if you were looking at separate dyads. And another study generalizes this to tree-like structures, showing that they cannot actually be reduced to serial chains. So therefore, network aspects are important. And then my second example is from the domain of disruptions. So most companies have visibility only to their first tier, and they don't know much beyond their first tier, and actually they delegate the control, the management to their suppliers, and these suppliers do the same to their suppliers, so it cascades through the network. And finally, as a result, each actor has only a very myopic view of the system. Therefore, the network aspect is lost. But what happened, for instance, following the Fukushima disaster, was that the auto manufacturer realized that almost all of them were reliant on a single supplier for a pigment for auto paint, which they were not aware at all. And this supplier was so critical that it led to disruptions. But if they had a systemic perspective, they had the visibility, and the system had been designed around this, they could have prevented this from happening. So network approaches are relevant for supply chains. So now I will introduce some basic network metrics and at the same time comment on its implications for supply chain. So let's start with degree. Which is the most fundamental metric. But for that, we first need to define directed networks and undirected networks. So a directed network has links which has a direction. So think about material flow. There's a supplier which sends the product to the buyer. So there's a clear notion of direction. In undirected networks, for instance, in partnership networks, those links are bidirectional, or they are undirected. So in directed networks, the in and out degree are the number of neighbors incoming connections or outgoing connections. Okay? So in the supply chain context, the in-degree centrality refers to supply load. And the out-degree centrality, on the other hand, corresponds to demand load. So what does it mean? It is the managerial and operational difficulty of having to deal with multiple firms on either the incoming side or the outgoing side, the demand side or the supply side. And for the undirected network case, the degree is defined as the total number of neighbors or connections. So in the supply chain context, what does it mean? For instance, in the contract networks, it defines, the degree centrality defines the influential scope, the impact on other firms' policies, because the better you are connected, the more influence you have on other agents in the system. And the closely related concept is the network centralization, which is based on the notion of maximum degree in a network. So we are moving from a node level to a network level. And in the supply chain context, this refers to network centralization. Central nodes refer to control and authority in the system, such as prime manufacturers, OEMs. And now we can talk about degree distributions, which characterize the distribution of degrees over the network. So we define it as pk, which is the fraction of nodes in a network with a given degree k, so which is plotted here in our figure. So the one with the dashed lines, the red one, refers to homogeneous networks which have a typical degree, so which is centered around the mean degree. On the other hand, we have got heterogeneous networks where there is not a typical scale. The degree might be spread over different scales, which means it is possible to find degrees with arbitrarily large nodes with arbitrarily large degrees, and these are called hub nodes, and they are very critical for any network and also for supply networks. In the supply network context, they refer to centralization, so it is the control and influence. They are the central nodes in the supply chain context. And now we have talked about degree, and our second concept is paths. So a path is, in a network, a path is a sequence of nodes that takes you from a source node to a target node. For instance, if we are looking at a path from node A to E, we have several alternatives. We can go directly from A to E through this link, or we might first go to D, then E, or first B to E, or first D, then C, then to E. But the shortest among these, as you have probably seen, is the direct one from A to E. Therefore, our shortest path from A to E is just one. And we define this shortest path for all combinations, all pairs of nodes in the system, say A to F, D to F, so on and so forth. And this information is key for the efficiency of information flow, because it's most efficient. The shortest the path is, the most efficient the flow is. And we have two key centrality notions about this. The first one is called betweenness, and the second one is called closeness centrality. And we will talk about them now. So the betweenness centrality is defined as the number of shortest paths that a given node X sits on. Say node D, how many shortest paths does it sit on, or the proportion of shortest paths that it sits on divided by the potential number of total shortest paths. And in the supply chain context, first in the material flow network context, the betweenness centrality has a very operational meaning. Because this focal node that we are interested in, we are looking at how many critical paths it is sitting on. Therefore, it has a direct impact on the performance objectives such as cost, quality, and delivery. And on the other hand, we have contractual networks, and there between centrality has a relational mediation meaning, because it is central to many linkages, and therefore it refers to power and network influence. And secondly, we have closeness centrality in the shortest path context, which is the inverse average of the shortest paths from a given network. Okay? In the supply chain context, or in general, closeness refers to how close a given node is to any nodes in the network. Okay, so it is about closeness. In the supply chain context, it can be interpreted as the informational independence, because it refers to access to information. And if you are close to all the rest in the network, then you have a good access to information, and therefore you have the capability to act independently. And a very related concept is the average shortest path length, where we take from the level of a single focal node to the network level and look at the averages of the shortest path lengths between any two combinations, pair combinations of nodes. And in the supply chain context, this refers to the responsiveness to demand, because the shorter it is, the more quicker to respond to changes in the market. And final metric that we will talk about is the clustering coefficient, which is about network transitivity, which is the propensity of two nodes being connected, given that they already have a common neighbor. For instance, it is here illustrated for the yellow node in the middle. For that, we define the local clustering coefficient, which is the number of existing links between any neighbors of the central node divided by the maximum possible. So here we have 4 neighbors, and among them there are 2 links, which are noted by red, and in total there could be 6, and therefore the local clustering coefficient is 1/3. And the global clustering coefficient is the average of local clustering coefficients over the network. And in the supply chain context, this has implications for flexibility, because if the clustering is high, then there are alternative paths that you can follow, alternative suppliers, for instance, which means there's room for dynamical rerouting and resource pooling. Therefore, it is good for flexibility. And also, it leads to extended information sharing, and therefore could promote collaboration or prevent opportunistic behavior because you have access to that information. So now, up to now, we have discussed the basic network metrics and their implications for the supply chain and supply chain management. Now we will talk about a particular process, network process, so-called percolation process, and we will also comment on its relevance for supply chains, which is the resilience of supply networks. So to understand or to define percolation process, we first need to define the network component. So a network component is formally a subgraph in which all pairs are connected. So what does it basically meaning? So it is a part of the network where you can find a path between any 2 nodes. For instance, here, if you look at the blue nodes, there is a path between any 2 nodes. And there's a second path, there's a second network component, which is the gray one. But as you can see, there are, on purpose I created that way, so their size is different. So if the network component is of the size of the network itself, then it is called a giant component. For instance, here, blue is meant to refer to a giant component. And now we can discuss the percolation process, having defined the network component and the giant component. In the percolation process, we are given a network. And on this network, with a certain probability, the nodes are made active. So let's call this probability P. And the rest are made inactive, and that's the complementary probability 1 minus P. So these nodes that are made inactive can be considered to be removed, disrupted. For instance, here, those ones that are shown by red. And our question is, what are the properties of the network of the remaining network? So we have removed the red ones, we have a remaining network, and what are the properties of this? And we are interested mainly in the network component. So is there a giant network component? For instance, here the one that's shown in green is the largest remaining component in the system. So we are basically talking about 2 types of node removals, node knocking down events. The first one, it is like errors, random errors. So the removed nodes are selected totally randomly. And in the second one, we have got target attacks, where the nodes to be removed are picked with their probability. So this is like virus attacks on computers, and the more links you have, the higher chance that, the higher risk that you will get attacked. And now, when we look at, so the response of the networks are very different to the percolation process. So for exponential networks, the response to random errors and target attacks are very similar. So if the connection probability is low enough, there are no giant components. It consists of many and only small components, which means the communication breaks down in the network. It is fragmented into very small pieces. And if the probability of connection is high enough, then a giant component is given birth. And of course, there will be small components, but they will join the giant component. And this critical probability is called the percolation threshold. But when we look at scale-free networks, we observe something very different. The response to random errors and targeted attacks are completely different. So when for the random errors in the system, the connection probability should almost be zero for large networks to break down the giant component, which means scale-free networks are extremely tolerant to random errors, which is very good for them. But on the other hand, this critical threshold is very high for targeted attacks, which means they are highly vulnerable to targeted attacks. And so what is the reason? The reason is mainly the hops, because in order to break down the giant components, you need to break down the hops. That's the main reason. And so what does this have to do with supply networks? Now, we have talked about removing nodes, knocking down nodes, which is actually very similar to disruptions, long-term lasting disturbances, which we call as disruptions. And these have become very common in the past 2 decades. And for instance, the disruptions introduced by the natural disaster in Japan, Fukushima disaster, or they might arise from local problems such as fire in a factory. And the complex networks approach can help us to understand how supply networks respond to such disruptions. So what are their resilience properties? And this has been looked into in the literature with using very similar approaches. For instance, the paper by Kim et al. And to understand how they would respond, this paper by Atalay et al. Is very informative. So they look at the structure of the manufacturing industry supply network. What they find is it is not scale-free, but it is very broad. So it is quite heterogeneous, although it is not fully scale-free. And now let's take it to the limit as if it is scale-free. Then the failures, and also consider that the failures would not be possible, would not be random, totally random in the supply chain domain, because the failures are load related. And therefore, if we think about highly heterogeneous networks, then they are very vulnerable against load dependent failures. And therefore, this introduces a potential explanation for high impact disruptions. But supply chain networks are not that simple. And therefore, we also need more advanced approaches. And several approaches have been applied to supply chains. So there is a very nice review paper by, an early review paper by Surana et al. Of different potential complex systems approaches that might be used to understand supply chains. And following this paper, so it reviewed existing applications, but also paved the way for future applications. And several applications have been made. For instance, one set of methods is called cellular automata. And it has been applied to supply chains in several papers. And also, agent-based modeling has been applied in the past 20 years. And its application is growing and growing. But we will not talk about these two approaches because they would require their own webinars. We will instead talk on two different approaches. I will very briefly mention an approach which is called MK Fitness Landscape approach. I don't know whether you are familiar with it, but it is a method that has been borrowed from ecology, which was introduced to understand the evolution of species. And then this was applied to the domain of business strategy. And recently, scholars are extending it to the supply chain strategy. The idea of fitness landscape approach is the strategy is defined as a vector of system states, where each entry represents an alternative strategy in that specific field. Say, for instance, distribution strategy, whether you are using channel intermediaries or not, for instance. And then the system, fitness levels are defined for each system state, and the system evolves according to the emerging fitness landscape and goes to the minima. But there are many local minima, so it is a complex process. So here it is such an evolution is shown. Now I will talk about another approach that has been very recently been applied to the area of supply chains by myself and my colleagues. So it is also borrowed from ecology, which has been used to understand the stability properties of large food webs. And supply networks are actually quite similar to ecological networks. So they are like ecosystems. And this approach is based on the dynamical systems theory and has a particular focus on stability. And it enables to capture specific flows. So it goes beyond, in a sense, than the percolation approach, because it defines the dynamical entities in the system. You can incorporate inventories, you can introduce price changes, quality changes, and then look at the idea of the approach is to predict the supply network response or complex network response to disturbances under general conditions. So it is called generalized modeling. And the particular focus is on identifying which parts of the network are most influential and sensitive. For instance, here the central one, which is red, is highly influential. So what do we mean by influential and sensitive? So let us define it to avoid confusion. So because they might be used to refer to different aspects. The sensitivity, we define it as the organizations being affected from changes in the system. So if an organization is highly affected from changes elsewhere in the system, it is highly sensitive. So it is very intuitive. And influential is if there's a change in our firm, if this affects other firms in the network very strongly, then this firm, this organization is highly influential. So we have used real-world networks, such as this one that I have shown. And by analyzing these networks, we have identified several patterns. So first, the effect of tier. So what we have identified is the upper tiers tend to be more sensitive than influential, which means maybe the disruptions here cascade more difficultly in a more limited sense, but they are very sensitive to changes elsewhere in the network. So one should respond, one should invest in the supply resilience capability, because there will be disruptions happening resulting from changes elsewhere in the network, and these nodes should be resilient enough. These firms, like raw materials suppliers, they should be resilient enough to recover back to normal operation. In the contrast, the lower tiers tend to be more influential. So we need to make sure that they keep healthy operation, and therefore we should invest in the robustness at lower tiers. And second result was on machining suppliers. So say a part is sent for some machining to a supplier, so it is not assembled, or it is like painting processes, for instance. So it is sent back to the manufacturer. And we have found that these meshing suppliers are highly influential and they have low sensitivity, which means they need to be very robust, and therefore they need to be closely monitored, which is important for the supplier selection process. And the further result that we have found is that stochastics, that stock inventories, are key for supply chain stability. But there are differences on the inbound and outbound properties of the stochastics. But these are the key result here is that stochastics are the key for stability. And with that, I would like to now refer you to some resources if you're interested in the topic. There are many books, many very good books, but I will mention just 3 here. The first one is by a pioneer in the field, Albert Parabashi. You might have heard of his name. So in this book, he discusses different applications of complex networks ideas. So it is very fun to read. I would highly recommend it. The second one is by another pioneer, Mark Newman. And it is a mathematical book and introduces all the concepts and key methods that are used in the complex networks area. And the third one is by Anna Naguli, which focuses on supply chain network economics and the dynamics of prices. So it integrates this approach with optimization as well. So it's a very nice book. And in addition to these books, so when it comes to networks, the network visualization and the calculation of metrics by softwares is done by several. You can use several different software packages for this, and this application is growing in several areas, as we discussed at the very beginning of the webinar. So I could mention 3, like Pajek, Gephi, Cytoscape, and also, for instance, R, general purpose software statistical packages like R. They have packages for network visualization and analysis. If you are already using R, then you can easily start analyzing basic properties of networks. So now we have reached the summary and conclusions. So we have first said that the complex networks is a universal approach for understanding systems from different domains. And supply chains can be modeled as complex networks, as in many other systems. And network metrics help us to understand the basic properties, supply chain properties, such as flexibility, responsiveness. And we commented that the supply chain management needs to be extended to incorporate network aspects, and actually this has been happening in the past couple of years, looking at a more systemic level, moving from dyadic relations to network aspects. And we have discussed the percolation process, which characterizes the attack and error tolerance of complex networks. And we have particularly talked about heterogeneous networks, scale-free networks, for instance, which are highly tolerant to random networks, but extremely vulnerable to targeted attacks. And supply networks are not scale-free, but they are highly heterogeneous. So this is a potential explanation of why disruptions have such high impact. And then we talked about different methods that can be used to investigate supply networks and to incorporate more detailed supply chain processes which lead to further insights. We have in more detail talked about generalized modeling, which provides what we call a systemic screening tool. So it is, we are given the basic properties of a supply network, and then we try to identify which parts of this network are more sensitive and which parts are more vulnerable. So with that, I would like to thank you very much, and we can continue with questions.
Thank you very much, Guven. So if you have any questions on that, if you would like to submit them via the questions box in the panel on your right. I've had one person ask if the slides will be shared after the event. Yep, they will be. They will be made available on our website as soon as possible. So while we've got people typing their questions, Guven, would you like to just give us another example?
Of course, and I'm very happy if you would like to contact me, if you are interested in the topic and would like to contact me. I'm very happy to get engaged. For instance, we haven't talked about network network cliques, which is a very hot topic. So identification of cliques in networks or community detection, and this has a direct implication for manufacturing domain. For instance, if you think about Italian production model, so there are very local, small, almost artisanal producers that are highly interlinked. So they form clusters in different geographical areas, and so this is, for instance, the constitutes one application or one understanding from the complex networks perspective. So do you have any questions, or may I continue discussing if you are interested? Sorry.
So sorry, Guven. I think you can carry on there. Yep, that'd be great.
Okay, of course. So, for instance, in this generalized modeling work that we have done, we have looked at the stability properties of networks, so which enables us to actually extend the definition of the elasticity. So elasticity is normally in the on the demand-supply relation, but by networks approach, we extend it to a network level. Then we have different types of elasticities. For instance, we have something we called co-supply elasticity or co-production elasticity, where a supplier has two different modes of production, say two different parts, or it supplies the same type of part to different firms in the same network, and therefore their production is dependent. And this is a very key factor for stability, network stability, and therefore the recommendation we developed is to trace the material flows to identify such co-production units which might constitute bottlenecks for the network, and build in extra capacity to these suppliers. Or in that application, what we have further found is, as the network complexity increases, although many things remain the same, actually some parts of the response are changing over the time, not over the time, or with the complexity. For instance, we call it elasticity to demand. So it is the change of the dynamics with respect to the demand level. So normally it has a stabilizing effect for small, simple networks. But as the networks get more complicated and more complex, it first loses its effect, and actually the effect is reverted beyond a certain point, which means it becomes destabilizing. So this illustrates the importance of networks approach, complex networks approach. So I'm very happy if you have particular questions.
That's great. Thank you, Guven. I think that's all that we've got time for today, unfortunately. Someone's come through and said that was very informative and enjoyable. So that's brilliant. And thank you so much for such an engaging presentation. As I've mentioned previously, the slides will be made available on our website for anyone who would like a copy. So thank you to everyone for joining us on our webinar today. And we hope you enjoyed it. Thank you.
Thanks a lot.